We're starting to switch gears. Today and tomorrow we're going to be talking about differential equations. Then we kind of close the class off with talking about vector calculus and reviewing its physics and its meaning. And then if we have time, we come back and do partial differential equations. The thing about it, this is kind of a transitional section because we're still going to constantly refer back to the linear vector space ideas. It's one way to think about differential equations from a physics point of view. So even though we will be doing sort of more traditional math things with differential equations, I will occasionally refer to the various linear vector spaces ideas because there really is a sense for linear differential equations in which you're really solving an eigenvalue, eigenvector problem, and it makes conceptual sense. So that's a good thing. Now, one of the things about differential equations that we don't spend a lot of time on up to now, and I'm just going to do this first part is just going to be really an introduction to it, but it really is why are we using them? What we are really doing is we're writing a model for how quantities change in time or space or both. The fact that the quantities are changing makes it a differential equation. That's why we invented derivatives to understand change. When they're changing in time or space, this is what we call an ordinary differential equation, or an ODE. And the reason for this is we have only a single variable that's changing, time or space, so we use total derivatives. If it's both, we have a partial differential equation, or a PDE. Now this can also happen if it changes in more than one direction in space, right? In space, would be a one-dimensional thing for it really to be an ODE. Once it's two or three-dimensional, we have partial derivatives because we have to worry about changes in x and y and z separately. So this is the goal of the differential equation. This is why they exist in science and physics. One thing we don't spend enough time on, really, is asking the question or making you write down the relevant differential equation. We spend a lot of time on solving them after we gave them to you. But as a professional scientist, it's picking the right one that often matters. So I do want to take a step back. And let's quickly ask the question. I've taken this example from Sarah Eichhorn because it's the best and most fun, which is the zombie apocalypse. So we have a bunch of humans who may or may not turn into zombies, both groups of which may or may not be removed permanently from the population. So if you wanted to model the evolution of the human population as a function of time, what pieces would be involved in this? So just pictorially, by drawing arrows, I want you to take a minute or two and answer the question of what is going to be required to model human changes in population as a function of time.
They're turned into zombies.
So yeah, do things like, if you think humans are turning into zombies, you draw an arrow from humans to zombies. That's what I mean by using arrows. So just laid out the arrows, the arrow diagram for this process. So go ahead and do it now on your paper or in your head. What are some arrows we have? Humans go to zombies. What else do we have? Zombies get removed. What else happens? Humans get removed. Any other arrows you want? What? So let's assume humans still reproduce. Anything else?
Removed, it becomes zombies.
Sometimes if you're completely removed, they do become back to zombies. That's an option. That depends on your method of generating zombies.
Zombies getting cured?
You could have zombies getting cured, and that would be much more like a standard disease model, right? And you could have zombies getting cured into two types of humans, right? There's humans that can become zombies, and then there are immune, which I think has two M's actually. Immune humans, right? Which immune humans can still die, but they don't become zombies. And that's a fundamental feature of disease. Often, if you've had a disease once, like measles or something, you don't get it again. Notice, this is something we don't spend a lot of time to, but for simple rate equation situations, it's rather straightforward to think through what your model might be. And one other thing you might consider is if you were only, say, modeling humans in New York and zombies in New York, you would need separate arrows for the flow in and out of the system. Now, in this simple model, what happens is all of these arrows get rate constants. So there's a rate k1 at which humans become zombies. There's a rate k2 at which humans are removed. There may be a rate k3 for the birth of humans and a rate k4 for zombies being removed. And I'm going to keep our model at that level. All of these other things are possible elements in the model. And part of modeling is to pick the ones you want to start with to keep it as simple as possible that you think are the most relevant. And all of these rate constants, or coupling constants, have time scales associated with them because we're doing things as a function of time. What is the fundamental time scale for humans to be generated?
A year?
Yeah, 9 months, a year, something like that. What would be the fundamental time scale for humans to be turned into zombies?
5 seconds.
Yeah, pretty much once you're bitten, it happens. So notice it could be that this interaction may not be relevant if these are happening fast enough. And that's one of the things we'd like to look at with our model. That's the thing we're interested in really in our modeling in physics, is less the solution of the differential equation. We know that effectively this is going to be some combination of exponentials in some way, approximately, because it's first order rate equations. But what's interesting is how the different rates affect things. What's also interesting is we know it's not quite purely exponential, because if I look at my various arrows and the way things go, what is the key thing about this term, for instance? If I start writing down my differential equation, I will have the rate of change of the human population, dH dt. It decreases because humans go to zombies, so that's a negative, proportional to the rate k1. And then what factor do I have here? If I'm going humans to zombies, what term shows up in the differential equation for that? What is that proportional to?
Amount of zombies.
The amount of zombies and the amount of humans, right? If I don't have any humans, they can't turn into zombies. If I don't have any zombies, they can't turn me into a human. They can't turn a human into a zombie. This is an interaction term. That's why I call it a coupling constant. It's an h times a z. Now, compare that to the rate at which humans are removed from the system. What is that rate related to? Just what? Just humans, right? They removed at some rate proportional to what they are. Now, let's think about the rate at which humans are created. K3 was our birth rate. What do I multiply this factor by? Humans. Now, it's also possible, depending on how complicated or detailed we want to make our model, we'd have to think about, is the relevant thing the way we're doing it humans or humans squared? Because it does take 2 humans to make a human. Or would we model men and women separately in the population? And then this would be men times women. And we just keep track of 2. And we'd have h equals m plus w and then this term would have m times w in it. So there's a couple of ways we could do that. Now, for the zombies, we create zombies at a rate k1hz, but they're removed at some rate k4 just based on the number of zombies. Now, that term might also need an h times z if it's only humans removing zombies, right? As opposed to them just naturally wiping out. So let's do that for now. Let's say the humans have to remove them. And then finally, things in the removed category are positive. And again, we have the h times z. And one of the fundamental features of a model like this is it's coupled, right? The variables depend on each other, but it's also nonlinear. And that's what makes the dynamics kind of interesting, is that there's a term that's not linear in the variables. It's quadratic in the variables. It's h times z. One thing that happens, if you think about it, if we were to do this with sort of an oscillating time, and there was some frequency that was intrinsic in the behavior, like if the population was oscillating at some intrinsic frequency, if I have e to the I omega t, and it ends up multiplying by itself, I get e to the I 2 omega t. This is what we call frequency doubling. So if you have an inherently nonlinear system, you can change the frequency involved. And notice that this progression keeps going. This has generated twice the frequency. That's going to generate 4 omega, and so on. And so there is this inherent nonlinearity that comes in. The other thing to notice about this is, what's the prospects for the human population if birth does not kick in?
Not good,
Not good. Why?
because they have nothing to replenish their population.
Exactly. Immediately looking at this, we see two negative signs. The rate only decreases unless K3 can kick in. And that's where the magnitude of these things and the time scales and the behavior becomes really important. And so looking at the structure of a differential equation, where it came from, why are those terms in there? Are there coupling terms? We call this a coupling, where you have the product of two things. That's a coupling term. And you can also have coupling between behaviors that's purely linear. This is a nonlinear coupling. I could have a term in here where dz dt just depended on something proportional to h, but not z. Right? Say humans spontaneously became zombies when they died for some unknown reason. Then you wouldn't need a zombie to generate a zombie. And I'd have a term here just proportional to h. And that would be a linear coupling between the zombies and the humans. These are the types of things that now, as you move forward with differential equations in physics, become almost more important to think about than the techniques of actually solving them. If for no other reason than to solve it, I just stick it in Mathematica and do dsolve if I'm stuck. Or ndsolve if I need to do it numerically. And that's why I wanted to kind of start with that example. Now, can someone name for me, well, any questions on that example that's disappeared from the screen? Okay. Can anyone name for me some other standard models that we use in physics that come up a lot of the time? Harmonic oscillators is a specific example that come up in what context? What are you modeling when you model a harmonic oscillator? Well, no. Which part of physics did that come up in?
It's like anytime you have a potential that's like
A square quadratic potential, but physically, what were you starting with?
mass springs.
A mass and a spring, and this is whose laws govern that? Newton's law with Hooke's law plugged in. So what you're doing is we're taking the basic, most fundamental model of mechanics, which is that forces are equal to mass times the change in velocity in time, or change in momentum, but we'll assume a constant mass. combined with the idea that velocity is dx dt, you put those two together and you get forces are m d squared x dt squared, and this is the piece that requires the modeling. If I have a spring, I put in Hooke's law. If I have gravity, I put in 1 over r squared. If I have electromagnetism, I put in Coulomb's law, and so on and so forth. We have lots of different ways to talk about forces, but we have this guiding principle, this overarching model that we know to plug it into. Similarly, current flow. Not quite as general, but a fairly general idea where we relate the definition of current being dq dt. Notice that's very similar to our definition of velocity being dx dt, a fundamental change in time. And that will allow us to look at situations where we have di dt in terms of the second derivative, d squared q dt squared. And now we have various models for current flow that show up, such as V equals IR, Q equals CV for a resistor and a capacitor. And we can take these and turn them into the differential equation that we need by plugging in the appropriate behavior. I is dq dt. Taking a derivative of this gives me a dq dt and a dv dt. And now I can relate dq dt's and build up a model for my circuit that's a differential equation. In quantum mechanics, this is where we really build in our linear operator connection. Linear operators for functions are very commonly represented by derivatives. So a central operator we deal with is the momentum operator, which is minus I h bar d by dx, for momentum, say, in the x direction, which allows us to write down the kinetic energy piece of the energy. And kinetic energy is what in terms of momentum? P squared over 2m. What is kinetic energy the way you learned it in freshman physics? 1/2 mv squared. But 1/2 mv squared is p squared over 2m. As you move to quantum mechanics, that's the more useful way to keep track of it. So as an operator, this becomes minus h bar squared d squared dx squared over 2m. And if you recall from what we did when we did linear vector spaces, these were both examples of Hermitian operators, which we'll find out in quantum mechanics has to be true. So that's another way in which we get modeling done and we use differential equations. The final piece, or a standard one that I'd like to mention, is how often flux and continuity come up. And this is a lot like what we did with the zombies. We have something in a box that has some density rho. And this thing can flow in and out of the box with some current J. And the fundamental governing thing, which ironically we'll do after we do differential equations, but do you guys remember what vector derivative determines how things flow in and out of a volume in space? I'll give you a hint. You learned the gradient, the divergence, and the curl. Which one tells me how things flow in and out of a box? The divergence, by its name. If things diverge, then there's net flux in and out. So the divergence plus d rho dt has to equal 0. And this comes from the fact that, notice that tells me the divergence is the negative d rho dt. If the divergence is positive, stuff is flowing out. So if this is positive, this decreases to keep it equal to 0. That's the convention for how we define the divergence. And very often, this flux, J, is given as the gradient of the stuff that you're interested in, or it's proportional to it. And by plugging that into there, I will get a second order partial differential equation for rho itself, because I'll have a physical connection between J and rho. And that's another This model models momentum flow and fluid dynamics and becomes the Navier-Stokes equation. It's a model for charge behavior. It's a model for diffusion of particles. It's a model for heat flow. Almost any situation in physics where you have a quantity that you want to know how it changes locally and you can associate a current with it, this is the equation you'll get. And the exact detail of it comes down to the physics that connects J with rho. And that's where the physics comes in. So that, I hope, motivates why and where what we're going to do with differential equations comes in. And it'll motivate kind of my approach to the pieces we focus in on for solving differential equations.